Okay. So up to last class, we discussed relation between electric field and potential. So that's the relation. The one is electric field is gradient of potential. If you differentiate potential, then you get field. The next, in this expression, the significance of negative sign is the direction of field is the direction of field is from higher to lower potential. This is the significance of this negative sign. And we also calculated, like, if we differentiate potential with respect to x component, then we get x component of field. If we differentiate potential with respect to y component, we get y component of field. If we differentiate potential with respect to z component, it's z component of field. So we get x component, y component, and z component of field. And if potential depends on all the coordinates x, y, z, on all coordinates, then we get all the components of field x, y, and z coordinates. If potential is zero, constant, that means your field is zero. This is what we discussed in the last class. Today we will start equipotential surfaces. The next topic is equipotential surfaces. So equipotential surfaces are those surfaces at every point of which electric potential is same. So equipotential surfaces are surfaces having same potential at every point. So those surfaces which have exactly same potential at every point are known as equipotential surface. So let's say this is an equipotential surface. So if this is an equipotential surface, then potential at every point, like if I make 2 or 3 points on the surface, this is point A, this is point B, this is point C. Potential at each and every point is same. VA is equal to VB, which is equal to VC. This is the definition of an equipotential surface. One example of equipotential surface is if you take a sphere. Okay, what is the expression for potential of a point charge? What is the expression for potential of a point charge? Jasola. Yes, Jasola. Do you remember the expression for potential for a point charge? Jasola, not very clear. Can you repeat again? KQ by R. So that's the expression of potential due to a point charge. So if I take a sphere, the radius of the sphere is R, and I place a charge Q at the center of the sphere. Then on each and every point of the sphere, each and every point of the sphere at every point, the value of electric potential is same. Potential will not change. On every point, potential is same. So we can say that surface of a sphere, if it have a point charge at the center, is an equipotential surface. So surface of sphere having point charge at center is equipotential surface. So this is the definition of an equipotential surface. If you take any surface which have same potential at every point is an equipotential surface. So take one example of sphere. If you take a sphere and you place a point charge at the center of the sphere, then potential at every point of the sphere is KQR. This is one example of equipotential surface. Now we have properties of equipotential surface. The first property is, if you take an equipotential surface, then potential at every point is same. Potential at every point is same. So if I draw an equipotential surface of any arbitrary shape, this is an arbitrary shape. I take 2 points A and B, then potential at A will be equal to potential at B. Second part. Electric field is perpendicular to equipotential surface. So if I take an equipotential surface, then electric field is always perpendicular to the surface. So if this is the surface, I take 2 points on the surface, then electric field is always perpendicular to the surface. That is the second property. Electric field is always perpendicular to equipotential surface. If you want to prove this, you can use the expression of work done. Only what is the expression of work done? How we calculate work done if field is given?
Sir, integral of F into ds.
That is for mechanics. For electric field, work done by electric field. Expression of work done by electric field.
Sir, Q delta.
So let's choose 2 points on the surface of the sphere. The separation between these 2 points is dr. So work done in carrying charge Q from A to B. See, this is the expression of work done. Now, we did work done in 2 methods. Like we did work done in the form of electric field also. So this is from where we started this chapter. This is the first thing that we did. This is work done by electric field E dot dx. This is how we calculate work done by electric field. So we can calculate work done using this expression also, E dot dx. And we can calculate work done through one more method. We also use this expression to calculate work done. That work done is this one, charge into potential difference. So we have 2 expressions to calculate work done. One is in terms of electric field, another is terms of electric potential. So I'll be using both. So I can write that work done is dW. A and B are very, very close points. So I call work done as a small work done. It's Q E dot dx. How we open the dot product, Hishma? Hishma, how we open the dot product?
E dx cos theta.
Yes, so that will be Q E dx cos theta. This is the first expression for work done. You can also calculate work done using charge into potential difference. Charge into potential at B minus potential at A now. Now, since both the points are at same potential, so they have same potential difference. So this VB will cancel this VA and this will be equal to 0. That is equation number. Now we can equate 1 and 2. Equate 1 and 2. So we have QE dx. Because we are calculating the same work done, just the paths are different. QE dx cos theta is equal to 0. Or you can say that cos theta is equal to 0. Or you can say that your theta is 90 degrees. So electric field is always perpendicular to equipotential surface. That's it. Third property. So third property is this work done in carrying charge across 2 points on equipotential surface is 0. So work done in carrying charge from one point to another over an equipotential surface is 0. Because potential is same, so work done will always be 0. Third property. See, if we try to relate electric field and potential difference, then we write that electric field is minus of dV over dr. So you can say that electric field is inversely proportional to the separation. Which means if you have equipotential surfaces, let's say you have 3 equipotential surfaces. Surface 1, surface 2, surface 3. In all 3 surfaces, potential difference is same. Like in 1 and 2, potential difference is dV. In 2 and 3, potential difference is again dV. Potential difference is same. That means if on the first surface, potential is 5 volt. Second surface, potential is 8 volt. The difference is 3 volt. Then what should be the potential on the third surface, Minashi? First is 5, second is 8, the difference is 3 volt. I'm saying between 2 and 3, potential difference is same. So if this is 8 volt, 11 volt. So that the difference between the potential is same, potential difference is same. If potential difference is same, that field is inversely proportional to separation. Which means if I call field in this region as E1, field in this region is E2, and these 1, 2, and 3 are equipotential surfaces. Okay, now can you tell me in which region field is strong, in region 1 or in region 2? Field is inversely proportional to the separation between the surfaces. So closer the surfaces, greater would be the strength of field. So field E1 will be greater than E2. So you can say that in region of strong field, stronger field, surfaces are closer, region of weak field, they are comparative far apart. The strong field hogi, so if field is stronger in a region, in that particular region, surfaces are close. And if field is weak, then surfaces are comparative far apart. So these are 4 properties of equipotential surface. Using these properties, we will be drawing equipotential surfaces for different charge configuration. Is it clear? Noha, Alia, Alvia, Anshika, any doubt?
No, sir. Yes.
Can you explain fourth property again?
Fourth property again. Okay. The fourth property says if you have few equipotential surfaces, so that difference between equipotential is same. Potential difference is same means on the first surface if it is 3 volt and I say that on the second surface it's 8 volt. So difference in potential is 5 volt. Then on the third surface your potential should be 13 volts. So that potential difference is same. Everywhere the potential difference is 5 volt. If potential difference is same, then strength of field will depends upon the separation of equipotential surface. Smaller the separation, greater would be the strength of field. So if I compare the separation between surface 1 and 2 and surface 2 and 3, so surface 1 and 2 are close. The separation is less as compared to surface 2 and 3. So in region 1 means between 1 and 2, field is strong as compared to the field between surface 2 and 3. Yes, Saifullah, is it clear? Saifullah, is it clear now?
Yes, sir.
Okay, just note it down. Then we will draw equipotential surfaces for different types of charge configuration. You have a test today at the end of the class, right? We already sent you text messages for it. You all have received that message, na? Anshika, Arpit, Mazia.
Yes, sir.
One minute, sir. Can you go up?
Yes, Arpit. Test is after the class.
Sir, it is like how much duration?
Sorry?
Sir, it is of how much duration? Like how long it will be?
30 minutes, 30 minutes. 10 to 10:30. A subjective test of 30 minutes. Written, everyone? Arpit, Yashika,
Yes.
Noah.
So,
Yes, sir.
1 minute, sir.
Tell me once you all have written. Huh? Cephala, done?
Done, sir.
Sure. So we have 3 to 4 types of questions based on equipotential surface. The question 1 is, draw equipotential surface for phosphor. The first is for a point charge. I take a point charge. Huh? So to draw equipotential surface for a point charge, we will choose all points which are at same separation from the point charge. So Anshika, if I choose points which are at same separation from the point charge, then what shape we will get? I'm connecting all points at same separation from charge Q. What shape you will get?
The circular.
Circular in 2D. In 3D?
Spherical.
Spherical. So if you have a point charge, then your equipotential surface is sphere. So all points which are at same separation from the point charge are at same potential. That's an equipotential surface for a point charge, spherical. Now we can draw many equipotential surfaces. Like we can draw first equipotential surface. We can draw second equipotential surface, or we can draw third equipotential surface. Okay, can anyone explain why as we move away from the charge, the separation between the surface is increasing? Can anyone explain why the separation is increasing as we move away from the point charge?
Because field decreases.
Yeah, because as you move away from the point charge, strength of field decreases. That's why the separation increases. That's for a point charge. Now, so for a point charge, the equipotential surfaces are concentric spheres. Concentric spheres. If you want to draw field also, then this is field perpendicular to the surface. See, field is radial. If you take a sphere and you draw radius over the sphere, then radius is perpendicular to the surface of sphere. After a point charge, if we take an electric dipole, what is a dipole, Noah? Noah, what do you mean by dipole?
So the system having a positive and a negative charge.
So dipole is a system which have equal amount of a positive and a negative charge. That's a dipole. So if you have a dipole and I ask you to draw the equipotential surface, so for one positive charge, the shape should be spherical. For another negative charge, shape should be spherical again. But there is some modification. See, first of all, positive and negative will attract each other. So due to attraction, the spherical shape will get distorted. So you will not get exact spheres, you will get ellipsoid. You will get this shape, not exact sphere, you will be getting ellipsoid. The reason of getting an ellipsoid shape is interaction. Positive and negative will attract each other. And due to attraction, the shape will change. Shape will be ellipsoid. The next is, if I take three regions, region 1, which is left to the positive, region 2, which is in between positive and negative, and region 3, which is right of the negative, then in all these three regions, the strength of field will be different. In all these three regions, the strength of field would be different. In region 1, field due to positive charge is away from the charge, and field due to negative charge is towards the charge. So in region 1, both the fields get subtracted out. Both are in opposite directions, so they will get subtracted. In region 2, due to positive charge, field is to the right hand side. And due to negative charge, field is towards the charge again to the left side, to the right hand side. So field gets added up. Both the fields are in same directions. If I take this region 3, in region 3, due to positive charge, field is in this direction. For negative charge, field is towards the charge in this direction. So as you can see, in region 1 and region 3, fields are in opposite directions, so they get subtracted out. But in region 2, fields are in same direction, so they get added up. So in region 2, strength of field is maximum as compared to 1 and 3 now. What about the separation between the surfaces? Alia, in which region the separation between the surfaces is minimum and in which region separation is maximum? Ali, I'm asking about the separation between equipotential surfaces. In which region the separation is minimum and in which region the separation is maximum? Okay. Minashi, in which region the separation between the surfaces should be minimum?
Region 2.
See, no, Alia. In region 2, the strength is maximum. See, fields gets added up. So when the strength of field is maximum, then the separation between the surfaces should be minimum. So in region 1, in region 2, surfaces are closer. Separation and strength of field are inversely proportional. See, in region 2, both the fields gets added up. In region 1, fields get subtracted. So here field is weak, here field is strong. So separation is less as compared. Similarly here. I'm asking about the separation. Huh? So separation is minimum. Field is maximum, but the separation is minimum. In region 1, field is minimum, but the separation is maximum. So these are the electric potential surfaces for an electric dipole. Third, instead of a dipole, if I give you two positive charges, you have one charge plus Q, you have another charge plus Q. The first surface will be ellipsoid. It should be spherical, but due to repulsion, shape will change. The first surface is a bit ellipsoidal.
There, ellipsoidal is like little curved.
Ellipsoidal means like ellipse, huh?
Yes, sir.
So ellipse in 3 dimensions, like circle and sphere, just
Yes,
like
yes,
that.
okay.
Ellipse and ellipse. So in region 1, both positive charges will generate field in a direction away from the charge. So this is the field away from the charge for first charge. This is the direction of field for the second charge. In region 2, field due to both the charges will be in opposite directions. In region 3, field due to this positive charge is away from the charge. Field due to first positive charge is again away from the charge. Fields are again in same direction. So in which region field is maximum? Mazia. Mazia, use chat room. Tell me in which region field is maximum? Region 1, region 2, region 3. Field maximum, field, electric field strength. Mazia, in region V1, see both the fields gets added up. In region 3, both the fields gets added up. But in region 2, fields are in opposite directions, so they get subtracted out. Right, Alia? Mazia, just try again. In which region field is maximum? Field will be maximum where it gets added up. Right. 1 and 3, huh? In region 1 and 3, fields gets added up, so the strength is maximum. In region 2, they get subtract out, so the strength is minimum. So region where field is maximum will have equipotential surfaces closer, and region which have comparative weak field which have surfaces comparative far apart. So in region 3, surfaces are close, so field is strong. Surfaces are close, field is strong. Region 2, surfaces are far apart, so field is weak. And then we can draw a single equipotential surfaces for both the charges also. You can draw a single equipotential surfaces for both the charges also. This is what we can draw also. Okay, Yashika, we draw a single equipotential surface for two positive charges, but we don't draw any such surfaces for electric dipole. Can you guess why? Why we can draw single surfaces in case of two positive charges, but not in the case of electric dipole? Yashika.
Sir, there is null point between them.
No. No, not null point. Noha, will you try? Ishma, should I repeat the question?
Yes, sir.
See, I'm asking why. See, we are drawing a single equipotential surfaces for two positive charges, right? You have two positive charges and we can draw one surface for them. But we can't draw such surface for a system having a positive and a negative charge. Why is it so? See, I can't draw a single surface for this system. Why?
As it
See,
will repel.
no. So the reason is if you have two positive charges, then both will generate positive potential. Potential will not cancel out. But if you have a positive and a negative charge, then positive charge will have a positive potential, negative charge will have negative potential. So these two potentials can cancel each other. That's why you are not getting a single equipotential surface for the system, but you are getting a single equipotential surface for this given system. Clear? Here both the charges are positive, so potential will not cancel, but here potential can cancel. Fourth part. So in the fourth part, we have a uniform electric field x-axis. Uniform electric field along x-axis. Alvia, what is uniform electric field? Alvia, what is uniform electric field? Alvia is not in class. Huh? Anshika, what is uniform electric field?
That every point the electric field is equal.
Yes. Uniform means the magnitude and the direction of field will not change. Both the magnitude as well as the direction of field are same. Such type of fields are known as uniform field.
And what about field strength?
Field strength is also same. Both magnitude and direction of field is same at every point. So we have a field along x-axis. So can you guess in which plane equipotential surface will lie? Field is along x-axis. So in which plane your equipotential surface? Open question to everyone. Field is along x-axis. Huh? I'm just asking the plane in which your equipotential surface will exist. It will exist in xy plane, yz plane, xz plane. In which plane your equipotential surface will exist? It's an open question. Array? Field is along x-axis. So which plane is perpendicular to x-axis?
YZ.
YZ plane. So equipotential surface is in YZ plane. So this is first equipotential YZ plane. This is second equipotential surface. That too is in YZ plane. Okay. What about the third surface? Say the separation between the first surface and the second surface. Let's call this as some D1. What about the separation between the next surfaces? Will it be same or different?
It will be same.
It will be same. Arpit says it will be same. Hishma, what do you think? You think it would the separation between the next two surfaces would be same or it will be different?
Be different.
Okay, can you say why? Why the separation between second and third surface would be different? See, same and different means separation between 1 and 2. Okay. And separation between 2 and 3. So we are comparing the separation between first two surfaces and next two surfaces. Yes, Ishma. Why do you think it should be different? Okay. See, how we relate field and separation, Ishma? How we relate field with the separation between equipotential surface? We relate field and separation between equipotential surface through this statement. Okay, when field is strong, surfaces are close. When field is weak, surfaces are far apart. Okay, now can you tell me what will happen? What should be the separation between second and third surface as compared to 1 and 2?
D1.
Yashika?
So can you explain? I didn't understand.
See, the separation between 1 and 2 is D1. I'm asking what about the separation between 2 and 3? Will it be equal to D1, less than D1, greater than D1? What will be the separation? This D2. Yashika?
Sir,
Field
it's
is uniform.
same.
Will it not be equal?
Yet it should be equal. Huh? You are right, Abid. Separation should be same. Because field, the strength of field is not variable. Na? Strength of field is
Yes,
fixed,
sir.
is uniform field. So you can say that D1 will be equal to the strength of field is not changed. Draw these surfaces, then we'll do more. Note it down. So Alia, the fourth point simply says the strength of field depends upon the separation between the surfaces. So if the strength of electric field increases, then the separation between the surfaces decreases. If the strength of field decreases, then the separation between the surfaces increases. This is it. That's the fourth point. Strength of field and separation between the surfaces are inversely proportional. That's it.
Sir, do we have to submit the test too?
Yes, yes, yes. On the same number from where you get this thing, the meeting IDs. They will forward it to me. Can I scroll it further?
Yes, sir.
So you have electric field which is increasing along y-axis. Huh? This is electric field is along y-axis. So this is your field which is along y-axis. So we'll answer. Noha, in which plane your equipotential surfaces will exist? Noha, field is along y-axis. So in which plane your equipotential surfaces will exist?
The exit thing.
Exit plane, right? Because surfaces are perpendicular to field. So perpendicular to, see, this is y-axis. So the plane which is perpendicular to y-axis is, see, this is y-axis. Huh? So the plane which is perpendicular to y-axis is this, and this is your exit plane. So the equipotential surfaces are exit plane. So we know in which plane your surfaces will lie. This will be in exit plane. This is your exit plane. This is first surface. This is your second surface. And this is the separation between the two. Let's say D1. So Hishma, now again the same question. Huh? Let's draw a third surface. This is first surface. This is second surface. I have to draw another surface, third surface. What will be the separation of second and third surface as compared to 1 and 2? Will separation remain same, increase or decrease? Hishma?
It will remain same.
It remains same. See, electric field is constant or it's increasing, Hishma?
Increasing.
Increasing. And how you relate strength of field and separation between the surfaces? Hishma, what's the relation between the strength of field and separation between the surfaces?
They are inversely proportional.
Inversely proportional. So if field increases, then what should happen with the separation?
It will decrease.
So what should be your answer? What will be the separation between 2 and 3 as compared to 1 and 2? Separation will remain same or it will decrease?
It will decrease.
It will decrease. Now you get the point. Huh? So this is exit. Alia, is it clear? So, okay. So these are few questions on equipotential surface. You already have written up to here. Just note it down. So that was about equipotential surfaces. Next, we will start potential energy now. So see, second chapter have 3 parts. The major part is potential, which is over. The second smaller, comparative small part is potential energy. And another major part is capacitance. So we'll try to finish potential energy today so that we can start capacitance in the next class. Yes, written. Shafula, Arpit.
Yes.
That's
Okay, let's move on to the next slide. So after potential, the next is potential energy. Potential energy. Now let's first discuss what is potential energy. General thing about potential energy. See, mechanical energies is of 2 types. One is kinetic and other is potential. Kinetic energy is due to motion of particles. The cause of potential energy is conservative interactions. So wherever you have conservative forces, you have potential energy. So if you have gravitational force, you have gravitational potential energy. If you have electric force, you have electric potential energy. If you have magnetic force, then you have magnetic potential energy. So wherever you have a conservative force, you have a potential energy. So if you have two charges, charge 1 and charge 2, they interact with each other. Interaction means they exert force over, interaction means force. Huh? So if two bodies exert force over each other, and if that force is conservative, then that system will have potential energy. If that conservative forces is gravitational, then your system will have gravitational potential energy. If that conservative forces is electric, then you will have electric potential energy. If that conservative force is elastic like spring, then you will have potential energy of spring. Just name a conservative force and you will have a corresponding potential energy. Now, how to calculate potential energy? To calculate potential energy, we use work done. We basically use this formula that change in potential energy is equal to the work done by external force, or it's negative of work done by internal force. So this is a general formula to derive all types of potential energy. This is how we derive potential energy in physics. We take work done by external force from one point to another. That work done will be equal to potential energy difference now. Or if you are calculating work done by internal forces, then negative of that work done will be equal to potential energy difference. So let's calculate potential energy of a system of 2-point charges. I need potential energy of a system having 2-point charges. So the definition is you just calculate work done in carrying these charges from their infinite separation. Work done in carrying charges from infinite separation to their respective positions get stored in it in form of potential energy. So the work done in carrying charges from their infinite separation to their respective positions gets stored in the form of potential energy. Or you can say that work done to make the system gets stored in form of potential energy. See what these definitions mean. Say you have, this is your coordinate axis, x-axis, y-axis, and this is infinity. At infinity, you have two charges. One is Q1 and another is Q2. These charges are at infinite separation with respect to each other. Now the question is it a system? Two charges at infinity? Yashika, what do you think? We have two charges at infinity. Is it a system?
No, sir.
Why? What do you mean by system in physics? What do you mean by system in physics? When I say a system of two charges, a system of two charges means two charges will interact with each other. Two charges will make a system if they interact with each other. They will make a system when they exert force over each other. If you have charges which don't interact, which don't exert force over each other, they don't make a system. They will make a system only if they interact. So if you have two charges that is infinite separation, they don't interact with each other, so they don't make a system. To make a system out of them, you have to bring them from infinite separation to respective position. Is this statement clear? What do you mean? What we mean by system in physics? Anshika,
Yes, sir.
can you explain again? What do you mean by system in mechanics?
That like if there's a system, then the two charges will like interact with each other. Then only it will be a system. Otherwise, it won't be considered as a system.
Right. So two charges will make a system only if they interact. Only if they exert force over each other. They don't exert force over each other, they don't make a system. So you have two charges, Q1 and Q2, they are placed at an infinite separation apart. What we do is we bring charges from infinity to finite position. We bring Q1 from infinity to a point A. Maybe the position vector of point A is R1. See, when you are bringing Q1, there is no other charge. Is there anyone who can repel this Q1? Only. See, both Q1 and Q2 are infinity. I'm bringing Q1 from infinity to this point. Is there any other charge, Puneet, which can attract or repel Q1?
No, sir.
So what will be the work done to carry Q1 from infinity to A? Think. There's no other charge here. So what will be the work done? Work done to carry Q1 from infinity to A.
Sir, कोई force नहीं है तो zero.
Very good. Work done will be zero. See, there is no force to repel or attract this Q1. There is no force which will oppose the motion of Q1. So there is no opposition, no opposing force. Work done will be zero. It's like I ask you to push a body on a frictionless surface. If there is no friction, then you don't need any force. Your work done will be zero. So work done in carrying charge, W1 from infinity to A will be zero. This is zero work. Is it clear? Noha, Hishma, Minashi?
Yes, sir.
Work done is zero because there is no other charge which will repel this Q1. So there is no opposition, so work done will be zero. Now let's carry this Q2 from infinity to A. Let's carry this Q2 from infinity to A. Q2 from infinity to A here. And the position vector of this point is P. Now I need work done. See, we are making a system. Na? We first bring Q1, then we bring Q2, then we'll say, okay, now Q1 and Q2 are interacting, we get a system. Work done to carry Q2 from infinity to B. Let's call this as W2. W infinity B. Yes, will there be any interaction now between Q1 and Q2? Saifullah, will there be any interaction between Q1 and Q2 now? When you're carrying Q2 from infinity to here?
Yes, sir.
So what do you think? What should be the work then? Will it be zero or non-zero?
So there will be no interaction.
There will be non-zero.
There will be an interaction. Arpit. This is Q1. This Q1 will repel this Q2.
Yes, sir. Yes, sir. Yes, sir. Okay.
So there will be a work done. Now the question is how to calculate that work done. How to calculate this work done? Alvia, who will tell? I need this work done in carrying charge Q2 from infinity to this point B. Can you just suggest me a formula to calculate this work done? Yoshika, give me a formula to calculate this work.
Q into delta V.
Yeah, Q into delta V, perfect. And which Q? Q1 or Q2? Q2, na? Q2 potential at B minus potential at infinity. How much is potential at infinity? Potential at infinity is 0. So your W2 will be Q2 into VB. And how much is VB? VB is the potential at B due to this Q1. Let's call this separation as R. So what is the expression of VB now? Say Q1 is a point charge. We are calculating potential at a separation R12 from the point charge. What will be the expression? Arpit, what will be the expression? Potential. Alia, potential at point B due to charge at point A. What will be the expression of potential? Okay. Yes, good. So it's K Q1 by R12. This is the potential due to a point charge. Nah? You're calculating potential at a separation R12 from the point charge. So that's K Q1 R. So this is the expression of work done. It's K Q1 Q2 divided by R2. Now this work done will get stored in the charge in the form of potential energy. This work done. Now let's calculate total work done to make the system. Next, total work done to make the system. Total work done to make the system. So the total work done to make the system is nothing but W1 plus W2. So how much is W1? It's 0. W2 is this K Q1 Q2 by R12. So this is the total work done to make the system K Q1 Q2 by R12. But this is work done to make the system, but we want to calculate potential energy. So the definition of potential energy says this work done, the work that you are doing to make the system gets stored in the system in the form of potential energy. See, you are spending some energy in bringing these charges. To bring Q1, you spend nothing, but to bring Q2, you spend some energy. That energy gets stored in the system in the form of potential energy. So you can say that potential energy is K Q1 Q2 over R12 now. So this is the expression of potential energy. K Q1 Q2 by R. So this is how we calculate potential energy for a system of 2-point charges. While calculating potential energy, keep this thing in mind. If you have a positive charge and you have a negative charge, potential energy is a scalar quantity. Then keep this negative charge with its proper sign. Use this charge with this negative sign. Okay. This negative sign will tell that force is attractive. So, okay, this is again from class 11th. If your force is repulsive, if you have a repulsive force, for repulsive force, potential energy is positive. But if you have an attractive force, your potential energy will be negative. So for a repulsive force, it's positive. For an attractive force, potential energy will be negative. So while doing your calculations, always consider the sign of potential energy. Note it down and tell me if you still have any doubts. Mazia, doubts?
Tell me once you have written, I will scroll it down. Can I scroll it further?
The 1 minute is over.
Sorry.
Scroll up.
Okay.
Okay, I'm sharing the questions now for the test. Yes, everyone have written?
Yes, sir.
Sure. No need to write the question. Just start writing the answers. Huh? Question 1. Define Gauss law and derive expression of electric field due to a line charge. Next, this is question number 2. This is question number 3.
So should we write the questions?
No need to write the question. Just start writing the answers. This is question number 4.
Sir,
Yes.
sir, in these MCQs, like we have to show all the
Yes. You have to write all steps.
Okay, sir.
It's a subjective test. Huh? Yes, Amna is a line charge. Line charge.
सर थोड़ा zoom in कर दो.
Yes, yes. You have to write the complete solution, huh?
Excuse me, sir.
Yes, Arpit.
Sir, in the third question, sir, I am getting answer, sir, 0.7. Sir,
Okay. And that option is not in the question, huh?
sir, but it's close to 0.6. So,
You're getting what?
sir, 0.7 N.
Okay, just write the option that you think is most appropriate. And I need complete solution. Huh? And
Yes,
just do
sir,
one
yes.
thing. See, on the top of your answer sheet, please write your name, subject, class, and also the name of faculty. Huh? Azam. Also write the name of the faculty. And then once you have finished with the test paper, just take a pic of this and WhatsApp on the number from which you get your invitation, class invitation. Huh? And please don't cheat from anywhere. Huh? You all have finished up to question number 3?
No, sir.
2 is done, na? Only Minashi.
Yes, sir.
Sir, wait, I'm writing the answer. Sir. First, I do third question.
Well, I need each and every step of you, huh? Right? All steps. I don't need just options. I need complete calculations.
Yes, sir, you can scroll.
Sir, can you show the last question?
Yes, Abid. Which one is not visible? Fourth.
No, sir, it's good. Excuse me, sir.
Yes, Arpit.
Sir, in the last question, we have to write the full explanation. What is the reason behind it?
Yes, just 1-2 lines why you choose a particular option.
Okay.
Sir, can you show question number 2?
Sir, I've sent the answer. Can I leave the class?
Yes, Minashi, Hishma, Saifullah, done. Okay, question number 2. Yes, Saifullah, done?
1 minute, sir.
Okay.
Done, sir.
Okay, then please send the question paper on the WhatsApp number. So we'll discuss this paper in the next class, and I will share the check sheets also.
Can I leave now?
Yes, sorry. Yes, Minashi, just share it on the number from where you get the invitation, meeting invitation.
Submitted.
Just share it on that.
Submitted, sir.
Sorry.
I submitted.
Okay, submit it. Okay, so now you can leave class. Test is over.
Thank you.
Thank you. Ishma, did you submit this your answer sheet?
I'm submitting, sir.
Sure.
Done, sir.
Yes, Ishma. So you have submitted your test?
Yes, sir.
Okay, now you can leave. Thank you.
Thank you, sir.
Saifullah, you're still solving your questions? Saifullah.
Done, sir.
Yes, Saifullah. So, you submitted the test. Saifullah, you submitted the test. Saifullah, have you submitted the test?
Sir, I sent it, sir.
Yes, Saifullah. You submitted?